Hey there and welcome. My name is Sandra, and today I decided to make a podcast with one man that is pretty damn good with graphics, and it's Matt. So, welcome, Matt. Thank you for coming.
Hello.
So, yeah, tell us, how have you started with the graphic? What was your experience? How did you make it to it? You have over 10 years of experience.
Yep. So the way that I started was actually um, when I was very young. I had a little bit of a problem getting um, enough money to for a decent gaming rig, uh, and I also wasn't allowed to own a console because you know my parents were psychiatrists, so explains a lot of things. And basically, the problem was that I couldn't afford a decent gaming rig, so I couldn't play all of the latest games. So, with nature being the mother of necessity, I decided to make my own. Um, Making my own games hasn't panned out that well. However, in as a kind of like a tangent, I got into graphics programming. And the reason for that is because the most kind of envious thing that I was about the new games that were coming out were mostly how good they looked and not necessarily anything else to do with them. So whenever I had money, I would usually upgrade my graphics card and not my CPU. So there was this funny moment where I had in 2007, 2008, I had a NVIDIA 9600 GT,
Mm-hmm.
slightly overclocked. But to go with that, I had an AMD Sempron, which was 1.8 gigs or some gigahertz or something like that. So my GPU could play Crysis, but my processor couldn't. So
All right.
it was a really funny predicament. So basically, uh, I was basically too young to kind of put a project together, a well thought out and well planned out project. Uh, so me making games has turned into me making graphics demos with absolutely no gameplay. Um, and that's kind of like shaped the focus of what I do, because my company doesn't make games. We mostly make graphics for games or for anything else. Um, for example, enterprise computer-aided design software. Because graphics is what has tickled my fancy, and I don't find gameplay programming or AI nearly as interesting or challenging.
Okay. And how have you started with the Ehrlich engine?
Um, it was the reason was actually quite simple because I started programming by learning a little bit of Python, but Python kind of has this really awful thing about indentations and the syntax is really awful. Um, and I basically wanted to make the best looking thing I could. So I kind of knew that basically I'd have to work directly with the graphics API because I wanted to basically not use like a library. Not that there were many at the time, but I wanted to have proper 3D graphics. So when I was a kid, there used to be this program called Game Maker. And the thing about Game Maker is was before version 6 or something like that. So it couldn't do 3D back then. It could only do 2D. So I made a number of arcade games, and those were actually the only finished complete games that I made, like actual games with collision detection, scores, and where you could actually progress level to level. And
All
there was
right.
one game that I made which had like really weird, like absolutely no story, nothing. But the the funny thing was that it was basically like an amalgamation of 6 levels where the gameplay in every single level was completely different and disconnected from the next. So one level it was like Space Invaders or some sort of like a flying Bulletstorm game, while like the next level was a platformer or something like
All
that. So that
right.
was
So,
the
so I
that
just got some random ideas from it together and said, all right, that's a game.
yeah, I mean, it was just like
Okay.
whatever was like okay to play. I mean, it just because back in the day, stuff like Miniclip and so on were really popular. Like we used to play that at school, and bear in mind those were like things that I made when I was like 11 or 12. So you
Mm-hmm.
know, it's like you spend your lunch breaks, in the library playing some Flash games on Miniclip, and then you're like, okay, well, I mean, it's just flying and shooting things, so I guess that's what I'm gonna do.
All right.
I didn't have the privilege of owning a console and playing many of the AAA titles. Although I did play some games which were AAA, like all of the Star Wars games. I remember Knights of the Old Republic was the only thing that would be playable on my shitty PC. So we're talking about, GeForce 2 or GeForce 4 with absolutely no shaders. So back in the day of 2004, 2005, so, that was like a triple A game that I played. I obviously played Quake as well, and I, yeah, I think I played Doom once or twice. But yeah, I mean, Doom 3 came out in 2004, and that thing I didn't get to play, not because I was too young. I didn't get to play because I didn't have a machine that could run it until I was like 16. So we're talking like good few numbers of years after the release. And I mean, Doom 3 still looks surprisingly good, given that it was made in 2004. I mean, the lighting in that is just, I mean, there's no global illumination, there's nothing, that really complicated there. I mean, the normal mapping, light mapping, and just a few stencil shadows are enough to make it look well put together enough so that it can stand the test of time. Because there are some games which I just play, like, and they just hurt my eyes. Um, and I mean, they hurt my eyes like a lot. And a lot of games I can't play anymore because the bar has gone up
All right.
because
Gotcha.
they just look really really bad from from today's perspective.
All right.
Um, so yeah, I mean the way that this eventually came to Airlift was because Game Maker couldn't do 3D graphics. I mean, there was like a really advanced tutorial for 2.5D graphics, so you
Mm-hmm.
could do like a Doom style shooter. But the thing is, you couldn't put any 3D models into it. It was only like sprites. It was like Doom was 2.5D, and then you basically all of the monsters in Doom are just basically sprites that turn, right?
Yeah.
Depending on which way they're going. So there's absolutely no 3D in there. So I was looking for something that could eventually, deal with models and triangles. And I've tried a lot of things. The main issue was that I was so budget bound that to get a decent like experience out of a computer, I couldn't run Windows. Like Windows XP was just too slow. It just completely sucked up all of the resources and it just got all sorts of lags or spyware, malware, or whatever. So I like by the time I was a teenager, I went onto Linux only because that was the only thing that could run on my crappy machine. So what I needed was an OpenGL engine. So like naturally that basically pushed everything that had DirectX out of the equation. Um, so it had to be OpenGL and it had to be, relatively recent. So I've tried messing around with Dark Places, the kind of like a fork of the Quake free engine that was kind of used to make the only decent looking game that I could run on my machine, which was Nexus. But I mean, the amount of C code in there and that kind of how big it was a little bit too complicated for me to start kind of making things in it. And I guess I stuck with Airlift because it had really good tutorials. Uh, yeah, I mean, it did have it had really good tutorials at the time. So everything like built up step by step. So you could like kind of like digest it. Um, and the other thing was that it was just really, really, really big. And I think at that time, that was like the only moment in history where Airlift was slightly more popular than Ogre. And I remember that Ogre was a little bit heavier than Airlift.
Okay.
So kind of hardware, like hardware forced the choice of the engine, I guess.
All right. So when have you started like making changes in the early, like as you didn't want, or whatever you found out bad for it?
Um, the thing with Airlift was that when I arrived, it was already past its heyday. So its heyday was somewhere around 2006. I arrived 2007, 2008. And basically, Airlift was started by one Austrian developer who basically handed over the project to some other developers later on. So he was basically no longer involved. And from what I gather, he started doing it on DirectX 8 or DirectX 9. And one of the very big kind of focuses that I saw was basically the ability to load Quake-free scenes, or basically Quake models.
Okay.
And because of that, it was really kind of geared towards very last generation sort of things. So we're talking about things like, for example, BSPs, binary space partitioning trees, OCK trees, all sorts of stuff that were kind of basically aimed at when you would, try and like optimize the draws of triangles. So you basically maybe draw 500 triangles at a time and do all sorts of complicated culling and I mean occlusion queries weren't even like a fully used thing back then. And it was mostly written against the DirectX 8 API. And the the thing was that the engine was started somewhere I think in 2003, and then by the time I came around, it was like version 1.4 or 1.5, and I stuck around with it until version 1.8. And basically, the, the issue was that everything was kind of the whole API was written around DirectX 8. So if you looked at the API and all of the different functions that you had, you're just like, I can see how that maps to DirectX 8 if you knew what DirectX 8 was at the time. And the problem was that the DirectX 9 parts, they were tacked onto this API that was already like written for DirectX 8.
Okay.
So it was like an addition. And then by the time OpenGL came around, it had to do a whole bunch of gymnastics to kind of fit into this keyhole. So, for example, where OpenGL has stuff known as frame buffers, which are objects which hold collections of texture handles that you're going to render into. DirectX doesn't have that, DirectX 9. DirectX just lets you like attach the texture as a render target. So you've got, basically render targets and just put it into different slots. So, behind the scenes, it had to do all sorts of things for the OpenGL backend, like, create a frame buffer and then attach it to a texture. And then by the time they came around to do multiple render targets, where you could render into more than one texture at one time with multiple color channels, then that kind of became a problem. So yeah, I mean, the OpenGL backend was definitely an afterthought. And I think after I finished all the tutorials, I started, obviously Crysis came out. So I was just basically trying to replicate as many of the effects that were in Crysis as I could, possibly do.
What were the effects, for example?
Depth of field, bloom, screen space ambient occlusion, later screen space global illumination, all sorts of stuff like that. So the earliest kind of problem that I came to was the lack of, because it was all coded around DirectX 8 to DirectX 9, you couldn't access the depth buffer as a texture. So you couldn't even create a texture that was like of the depth format. So whenever you had a render target, you had to create like a special buffer, which was not accessible as a texture, and that was the depth buffer, and that was attached to the frame buffer. And the problem with that was it didn't give you access to it as a texture. So you couldn't then run a shader that would, for example, do depth of field. So, because you need to like calculate the circle of confusion depending on the pixel's depth and do like an adjustable blur.
Mm-hmm.
So I started, that was the first time I kind of started hacking around with using like OpenGL handles directly and so on. So that kind of got me started doing the first changes. And afterwards, it was just basically stuff that wasn't in there because it was part of DirectX 10. So,
Okay, and what hacks have you used, for example, to manage that?
Well, I didn't feel comfortable like changing the whole engine, so it was just basically like where you've got the OpenGL handle, just having a function that can pass it to you, and then you can do a whole bunch of stuff manually. But it was just
All right.
if you tried to use it for more than one thing, then the whole thing would fall apart because there's a whole bunch of state that you need to track. Yeah, and I mean the also like right after I got started, NVIDIA was nice enough to make GPU Gems a publicly available book. Because unlike the GPU Pro series or the GPU Zen series, where
Something disconnected, I think.
yeah,
All right.
headset just run out of power. So unlike the GPU Zen, GPU Pro, and before they were called something else. Oh yeah, Shader X. Unlike those books, which cost $100 a pop, GPU Gems was available online. So there was a bunch of things to do with GPU Gems 1 and 2 and 3. And basically, GPU Gems 3 was all about the DirectX 10 API and what it can do. So stuff like, geometry shaders, marching cubes instancing, all sorts of things like that. They introduced, and that you couldn't find, in Airlift or in Ogre, in anything. So if I want to have any of those things or try and do something using those things, then I basically have to like patch them on or add them on. And sometimes they were really useful things because on the forum people used to post patches they could apply to the source code. So stuff like, for example, occlusion queries you could patch onto the main engine. Yeah, so it was basically because of the GPU Gems books that I got any sort of graphics knowledge at all, because they were freely available.
All right. And what have you used when you started actually working on the engine? Like, what changes to optimize it, and what have you worked with?
At first, I didn't really optimize it that much, because it was mostly about the missing features. So you wanted to do something, but for example, a certain feature wasn't in there. So talking stuff about floating point textures for HDR, any sorts of stuff like that, it just wasn't in there.
All right.
So it was mostly about basically adding features. The first time I actually started to optimize was maybe when I got my first paying job, which was to fix some issues that were happening between Airlift and the Bing video player. And then afterwards, like the whole company went through some financial troubles and whatnot. And then at some point they decided it's a brilliant idea to basically throw out Bing and not pay the Bing license and play back all of the video based off FFmpeg with VP8, because VP8 doesn't have any royalty costs, unlike X264. So basically, I put together like a whole multi-threaded thing for, I think, less than $400. That's how much I got paid. So I put together basically, like a small library, maybe like 8 or 9 files, but I could in a multi-threaded fashion, it could decode multiple video streams from VP8, upload them directly to the GPU, and then run a shader to do the planar YUV420 to RGB8 conversion.
All right.
So that was like the first time I actually started to optimize things. So for example, direct texture uploads, because Airlift had a really funny API where for every single texture you had a CPU copy, and if you wanted to modify it, you basically what you do is you lock the texture, which basically means get a pointer to, and that's the whole thing that I meant about it basically following the DirectX 8 or DirectX 9 API really closely, because there's also a texture lock function there. So you'd lock the texture, get a pointer to the texture, change the few pixels, and then unlock. And then what would be behind this unlock is basically a re-upload of the entire CPU copy to the GPU without caring about anything really. So that was the first time where we actually started using like pixel transfer buffers and asynchronous texture updates for OpenGL.
Right, and how exactly, for example, the pixel buffers worked for you?
Um, well, I mean, it was a lot faster. The main thing was that um, you could kind of thread it. The main problem was that you couldn't thread texture loading, and you couldn't thread. Sorry, yeah, you couldn't thread the texture uploads because Elixir is like basically written with no thread safety whatsoever, and OpenGL doesn't, can't really use it from threads unless you fix all of the initialization to have different contexts and stuff. Um, so yeah, I mean the video decode was threaded and all sorts of stuff like that was threaded, but then the actual uploads they had to occur in the main loop. But using the pixel packing, sorry, the pixel unpacking buffer, what that does is basically it lets you schedule the texture update for later, because OpenGL takes a copy of the buffer that you want to update and puts it somewhere on the driver queue, which is kind of, your whole application doesn't stall because you've updated the texture.
All right. That's a cool way to actually optimize that. And can you like do that with the whole scene, or is that only for certain elements that you calculate somehow?
It was only for the textures that you wanted to be video screens. So they basically change every 16 milliseconds. Well, not 16. 24 times a second. They basically change however many times was necessary because of the video. So yeah, it was basically that. I mean, later on, after that kind of didn't go anywhere. A few years later, when I actually was at my second job, first big job, we implemented some TV screens in the game where you could basically click on a TV screen, you type in a YouTube URL, and then what the game would do would basically run a YouTube download script, download the movie from YouTube, so like an MKV file, the VP8 file plus the VP8 video plus the OGG audio stream, and basically download it onto your computer, and then once that's ready, it would actually start playing it in game on the TV. So it was a very, very similar system. It was clean roomed. So I basically wrote the whole thing from scratch again, but still FFmpeg. And this time around, I handled both the audio and the video part of it, the streaming. And this time was actually after I forked the Irlicht engine and made a number of changes. And then it was actually possible to use OpenGL from threads and have an upload buffer.
All right, and so, was it like fast or slow to actually download everything from the YouTube, even for one video?
It depends how long the video is, but most things would start playing after a few seconds because people would download maybe 5-minute videos or something like that. And they go onto your game folder and get cached there. So next time you ask for it, it doesn't have to download it.
All right.
So yeah, I mean the cool thing about this system was that the game engine, the game used Fmod for audio. So the same solution that Unreal Engine uses. And if you want to do streaming audio, audio that doesn't come from an MP3 file or from from disk or from an audio buffer in memory. If you actually want to continuously stream memory using some sort of a source, then it's not very clear and straightforward how to do that in Fmod. Because before, when I used to work on the same thing a few years back, what would happen is we used SDL audio and a whole bunch of other things. So they actually previewed that you might want to generate your own audio data. So you could actually make a source, which was basically a streaming source with a callback. But for Fmod, the way that you do it is you register a custom DSP filter. So it's basically after Fmod is playing back your audio, right? after it plays back, you can apply a custom DSP filter on top of the samples that go into the mixer for a particular sound source. So the way that we did it is basically you've got you've got like an empty sound thing which keeps on looping. So it's a sound source with maybe a few samples that keeps on looping, and then you register a custom DSP filter on top of that, and basically that thing is the callback from fmod. So fmod, every few thousand samples, it calls that to provide the filtering for the next few thousand samples. So instead of filtering, the empty input samples, what you do is you basically replace them with the ones that you can pull from like a concurrent queue onto which the video decoder with FFmpeg places the sound samples. And that was kind of cool because the fmod thread is a real-time thread, the FFmpeg decoding thread is a different thread, and the FFmpeg file demuxing thread is a different thread. So basically you've got an IO thread which kind of demuxes the file and has the packets, puts it onto a queue, and then you've got decoding threads which decode the packets. And there's a different thread for audio packets and there's a different thread for video packets.
All right. So when you were working on the engines and on your jobs, like, when have you learned about certain tips and tricks and best practices for like C++ and the graphic itself? That, for example, when I go sometimes on your Discord, I see some ways that you are trying to create certain things that are not something usual that you see in implementations. Like you're trying to use different approach than normally in like by everyone I've seen before.
Well, I mean, the main thing is that most people are constrained by getting the next product out of the door. And you also got a little bit of inertia, which is caused by basically all of the people who are already using your product and relying on your product. So, for example, if you are thinking about Unreal Engine 4, which is used by thousands or maybe even millions of developers, if you start breaking the front-end APIs, that's going to be a problem because you might invent the next best feature ever, but if you change it too much and then it takes a lot of time for people to learn how to use it, then you might have invented the next best thing after sliced bread, but the cost of actually the human cost, developer time of transitioning to this next best thing might be a lot bigger than just basically sticking with the old way of doing things. And also, if you're trying to run on like 8 or 10 different platforms, which is the case with Unity, then all the way from crappy mobile and Android TV and God knows what else, or for example the web, which is its own can of worms, then that really kind of shrinks the common set of functionalities that you're allowed to use, which is why custom engines still have like a right of. That's why they still exist, because for example, Unreal needs to have a unified API for your game. It's not like you're gonna have 8 different APIs depending on what platform you run on. But if you, for example, got an internal engine which is only designed to run on a PS4 or a PS5 or on an Xbox or maybe just on consoles, where like the GPU is made by AMD and it's mostly the same architecture, then that's absolutely no problem. Because you can basically restrict the domain of your problem, the domain of implementation, and just basically focus on that and get much better results. So yeah, I mean, with regards to the C++, I don't think I've actually made that much of I've certainly made progress in my first job, a lot of progress, but the real cool C++ tricks that I've started to see and kind of use, I think they kind of emerged a little bit while I was at university, a little bit while I was, trying to compete in my high performance computing course at university. And a lot of it, I'd say that I've learned a lot of C++ when when I was finally allowed to transition to C++11. So it was actually around the time that I hired my first employee, and he's like a real C++ passionate person. And in many respects, I'd say that I learned C++11 from my employee because I was stuck in C++03 land for a very long time.
Can you
And that's
give us
kind of
some examples of what tricks have you learned in the university, in the course?
I think a lot of stuff about auto vectorization that might actually happen with a compiler. I learned my SIMD and SSE stuff half from my job, half from university. So I mean a whole bunch of stuff about alignment, memory alignment. At university, basically SSE and stuff I learned at my job, but the other stuff that might benefit you, like for example, memory that's pinned to a page, or allocating your memory to start at a page, or for example stuff like false sharing, where if you've got multiple cores that are going to be touching the data which is around about the same address, the same cache line, then you're going to have a problem. And how that impacts systems where you've got multiple CPUs. I'm not talking about cores, but CPUs on different sockets. So the CPUs are no longer auto magically, viewing the cache as the same thing, but there's the non-unified memory model thing, and there's a Intel QPI which basically synchronizes the caches between two or more processors. And then kind of seeing how much the performance tanks from that, and stuff like thread affinity. That was kind of really important to see, because I think out in the real world where you're a game dev, you're never going to see that unless you had access to a PlayStation 4 or Xbox. Because, I mean, normally if you're a PC game developer, you never come across the case of where you've got two separate physical processors. You will obviously learn to multi-thread your things, but you will never have to consider stuff like thread affinity and non-unified memory architectures.
All right.
So
how, for example, you can handle that stuff?
I mean, on the PlayStation 4, and for example, if you're programming a server, what you do is basically you'd pin your threads to certain cores. And you can pin your thread to one core, so basically the OS can never wake it up on a different core and kind of have it resume its tasks. But you can also have like a thread mask. So, for example, on Linux, you can, for every single thread, you can. On Linux, it's actually quite hard, because if you want to set thread affinity for a long time, I think that's still the case, you need pseudo privileges, whereas on Windows and on the PlayStation you don't. But putting that aside, if you want to set thread affinity, you can basically set thread affinity to a mask. So if you know which cores correspond to which physical CPU, then you can say that, for example, this thread can only wake up on the CPU. And what that will do is basically it will only wake up on the cores which are physically on the CPU. If you get your mask right, obviously you need to calculate the mask. And it's really useful because the thread is never in a situation where it gets preempted, or for example, it goes to sleep and wakes up on a different core, which is a problem, because if it was already relying on a lot of data that was in L1, L2, and L3 caches, all of the data will have to get moved. Well, not exactly moved, but it's no longer in the cache, so basically you restart the thread, and basically every single memory access is a cache miss.
All right. So, what have you also learned when you're working all those years with Irrlicht? Now you change it to Nabla, like your own engine, working with your employees. What are the core things that you learned by the time you've worked? What have you learned to never do? What are the improvements, so on and so forth?
I mean, one of the things that you should possibly never do is begin to think and design your data structures so that they can be used by multiple threads simultaneously. Because either it's not going to work, or it's going to be really slow. So, you're not gonna get any performance speed up from firing up 8 threads which are gonna be doing the same thing on the same object. Because if you have shared data structures between threads, what basically happens is that you need to put a whole bunch of locks and waits and all sorts of things which basically prevent concurrent write access or even concurrent read access. So basically partitioning work into separate things, which basically one thread doesn't have access to the bunch of things that the other thread is doing, and basically where everybody has its own little piece of work which doesn't co-depend with another piece of work. That's very important. And that's also important when you're scheduling people. You don't want to put 2 people on the same task. So that's also something that I learn as somebody who employs 4 people and possibly more in the coming weeks. So yeah, I mean, this threads are the same as people. I mean, you wouldn't want to, I don't know, delegate 2 people to pack the same box of chocolates, right?
Yeah,
It's not gonna work.
that kind of makes sense.
Yeah, that's just gonna take more than if you just took 1 person to do it. So yeah, so that's pretty much like number 1 thing, and basically global variables are bad. Thread local variables are also bad because thread local variables are the same thing to fibers as global variables are to threads.
Mm-hmm.
And then on top of that, there's also basically static variables are not special. They are globals. They're just, they have scopes for naming. And that's the only thing about them. So yeah, I mean, and pass all of your state as explicit. So, if you're making a function that relies on some state, don't embed the state into the object. Have a separate context object. Because then, next time you call this function, if you call it from 2 threads, that's going to be a problem. Because, so, I mean, I'm not a great fan of functional programming. I think the procedural makes a lot of sense, especially not pure functional like Haskell. But I am of the opinion that all of the state, or basically the output of a function, or what the function does, should only depend on the inputs to the function. So if you have some sort of a state that needs to control what a function does, that needs to go into the function as a parameter, as some sort of maybe like a pointer to a constant context. Sorry, not constant, but I mean like a pointer to a context option or a context struct, something like that. Don't make stuff implicit.
Is that the reason why you don't like Haskell?
Is there a reason why I don't like Haskell? Because Haskell is basically very absolutist. So it basically says that what a function does should always be repeatable, given the same parameters. And the problem with that is it's just absolutely, well, it's not impossible, but you kind of have to go against that if you want to do anything like file reading and file writing. Because I mean, if you do file read and file write with the same file name, then by Haskell's assumptions, your program should always like kind of produce the same value. But if you're gonna open and then write append to a file, then that kind of depends on some implicit state that is outside of the program. It's outside of that function. So doing anything useful cannot be done with like a pure functional language unless all of the implicit state ever, like basically the previous contents of a file or something like that, you basically bake into this one big function. So I mean, to do anything in Haskell, like for example, OpenGL, or do anything like file I/O in Haskell is basically a total mindfuck.
All right. And are there like some lightning tricks that you've learned so far by working, like for example with the ray tracing, some ray marching, or anything?
I would say temporal supersample anti-aliasing is very nice. temporal reprojection is very nice. Well, whatever project you start or begin working on, you should definitely get that in, because there's just a whole bunch of things where you can just say, oh, we just make this stochastic and temporal reprojection is going to fix it. Or you can basically say, we're going to reduce the quality and that temporal reprojection is going to fix it.
And what's the temporal improjection doing exactly? Like, why is that fixing stuff?
Basically what it does, you keep a cache of a previous frame. You might just keep the previous frame. You might keep the previous resolved frame, which is basically the already filtered frame. Or you might keep a cache of previous frames which are unfiltered. Nowadays, we mostly do it with already filtered frames because of the bandwidth and the memory constraints. And also that if you keep a previous frame, it kind of has like this geometric average behavior, where basically you slowly blend all of the previous frames together, as except for, last n frames if you keep them unfiltered. But basically what temporal reprojection does, it reprojects the current pixels into previous frames locations and looks them up in the previous image. And then tries to use the information from the previous image to improve the quality of the current image. Which makes a lot of sense, because, I've even thought about this when I was 14. I was like, why are we, like, if something doesn't move in a frame, why are we drawing it every frame? Right? So, like when you've got like a city landscape and maybe only some characters move or something like that, why every frame do we redraw the city? Right? So what temporal reprojection anti-aliasing does is basically, it doesn't stop you from doing the extra work, but at least it improves the quality. So by applying a jitter, or just basically by the virtue of the camera moving a little bit, you can blend previous pixels together, which helps with the aliased edges. It helps with specular aliasing, for example, when you've got really shiny surfaces. If you want a real nice example of a game where you can see specular aliasing, you should play Metro 2033 and Metro Last Light. Even the Redux editions have specular aliasing, mostly because back in those days they didn't really do a lot of research into how to filter the mip maps of a specular texture in the normal map, of a roughness texture in the normal map. But yeah, basically temporal anti-aliasing would help with that. It will help you with it might even help you with stuff like screen space ambient occlusion. So normally what you do is, to get the ambient occlusion, you'd do a few samples around the pixel, kind of estimate how occluded it is from the positions of the other pixels around it. But the thing is, you can't check every single pixel around it, because that would just take too long. So what you do is basically you have a sampling pattern which is kind of random, and the pixels they have gaps between them. You don't check every single pixel, and because of those gaps, there's a lot of noise. It's because sometimes you might miss a feature, but in the next pixel over, it might actually hit that feature. So you've got the grainy noise. And what has been the technique for ever since screen space ambient occlusion was used in games, which was 2007, 2008, up until 2016 or even 18, is basically, we're going to take this noisy image, which we have computed at half scale anyway, or maybe even quarter scale. And what we're going to do is we're going to blur it, but in a way that doesn't cross any edges. And then we're going to upscale it, bilinear upscale, which is like a clever upscale where you basically take an average of the four surrounding pixels, but try and not use the pixels which that are on a different surface. So that's the way that was always done. So obviously this screen space ambient occlusion doesn't get you any of the really tiny features, and it's not very sharp. It's very kind of like washed out. So what you can do instead is you can actually do the screen space ambient occlusion at full resolution with even less samples, and obviously get horrible noise, But because the temporal anti-aliasing reprojects, an infinity of frames behind, or maybe on average 16 or something like that, and you've got the jitter pattern, then what happens is that when you resolve that, you can get an image which looks like you've used 16 times as many ambient occlusion samples. So you can basically save on the bilinear upscale and on the blur filter, which was supposed to remove the noise from the ambient occlusion. And that's really powerful. Temporal anti-aliasing is basically like a very primitive denoiser. For ray tracing, we've got other things which work a lot better. But temporal anti-aliasing is very simple, and you can leverage that not only for ambient occlusion, but you can also leverage that even for lighting. If you, for example, decided to evaluate the light for every 16th pixel, and then over the course of 16 frames, you changed which of the 16 pixels it's going to be. So if over 16 frames, if you didn't move the camera, you would have eventually calculated the light for every single pixel, and you boost the light by a factor of 16, then what temporal anti-aliasing would do, or a denoiser, was basically blend all of those 16 frames, backwards in time after reprojection, and you'd pretty much get the same result as if you are always doing the light calculations for all of the pixels, not every 16. That's really powerful, because what it enables you to do is either have the lighting portion of your game take 16 times less time, or you can have 16 times as many lights, or maybe 16 times as big a resolution for the same cost. And the only reason we don't do that right now in games is because shadow mapping is still popular. That would be a lot of wasted effort to basically to do the shadow map without any gaps, only then to stochastically evaluate the lighting. But it's something that we do with a ray tracer on a daily basis. If you have a ray tracer, you don't actually evaluate all the lights. You pick a certain number at random out of how many lights you have, and then basically either keep on doing that until you get a reasonably converged result, or apply denoisers and temporal reprojection.
All right. So, do you think that it will replace the shadow mapping in the future?
Yeah, I'm definitely confident that ray tracing will replace shadow mapping for 4 different reasons. One of them is shadow mapping is very constrained by the linear projection that you have. There are some things like rectilinear warp shadow maps, where basically through tessellation and all sorts of other things, but there's a whole bunch of hacks. You need to chop up the triangles. You can kind of squeeze certain parts of the shadow map and then expand others. But it's still rectilinear, so it's not like you can blow up a certain point and blow up another point without any repercussions, because it's all kind of coupled together. If you blow up this point, then you can't shrink this point. The only way that if you expand this area here like this and like this, then this area here is going to also like expand like this. So you might be able to shrink it like this, but then this area is depending on that. So rectilinear warps, they improve the distribution of pixels a lot, but it's not like a magic solution. There's also adaptive shadow maps, where you render the scene, you figure out which pixels you can see, and then you build a bounding box of them in light space. So then you can crop your shadow map only to the bits that you actually could see with your camera, which is, it's really awesome if you're in a city or in a car, like I am right now, and the only thing you're seeing is basically the next wall over and the car, and you're not looking at the valley, down in the distance. And that's great as long as your viewport is like that. But the moment you turn over to the valley and you can kind of see a little bit of everything, then this gain disappears. You can obviously combine adaptive shadow map with rectilinear warps, but then that's two compute shaders. And then you can also combine that with cascaded shadow maps, where you can chop up the stuff into cascades. But still, there's a number of things which are going to present problems. So dueling Frosta is going to present a problem. So when you've got a Frostum where all of the resolution from a camera is kind of concentrated in this little area, and then as your field of view grows bigger, then every single pixel is a little bit bigger in world space. And then if you've got your light caster from the other direction, we're talking about an actual light, not the sun. The sun's rays are parallels. So if you've got like a really strong light, like let's say you wanted to have a searchlight in the game, right? Then the resolution of the shadow map is going to be all concentrated on near the light. So the texels of the shadow map are going to be really small in world space here, but really big here. And then if you've got dueling Frosta, well, basically what means is that you've got them set up against each other. So the very big shadow map texels are going to be where they need to be the smallest, which is where the texels that your camera sees are going to be very small as well. And the problem is that you've got a big shadow map texel and a small screen space texel. So that's dueling Frosta. And for example, cascading shadow map only solves that problem a little bit. Basically, it mitigates it, but to really mitigate it, you would need a lot of splits in the cascade, and that's kind of an issue. And I mean, cascaded shadow mapping is really expensive, so because you basically need to draw 4 times. You're not drawing everything 4 times, but you still need to do the culling, all of the stuff for all of the objects to kind of figure out which objects are going to be inside. And nowadays, it's the bottleneck is not as much how many triangles or how many objects you're drawing, is mostly about how many times you swap the render target. So yeah, I mean, cascaded shadow maps are really expensive, and then they're only used for big, very important lights, like sunlight and so on. Not really, for every single light. You're not going to use it for every single light. Yeah, I mean, you've got light perspective shadow maps, which is basically a warp to the shadow map, which gives you more resolution close to the viewing camera. But again, it can't deal with dueling Frosta. It can't help you there. Rectilinear warp shadow maps, that might help you a little bit by, if you've got dueling Frosta, it's going to basically grow the middle portion of the shadow map. So that's going to help you there. And adaptive shadow maps are going to help you as long as you don't have like a very wide field of view. So it's a little bit like occlusion. It's a little bit like occlusion culling. It works great for first-person shooter games, when you're in buildings and stuff. But when we're talking about, for example, Microsoft Flight Simulator, there's not going to be any occlusion. Because, I mean, if your point of view is high above ground, nothing occludes anything. Even like a mountain doesn't occlude another mountain. So that's kind of like an area where for all of the shadow mapping, you're going to be completely screwed, because there's just no way to reconcile it. And there's also like a lot of area and shadow maps that gets absolutely unused and is completely not necessary.
For example?
I mean, if you had like a shadow map, right, and you've got like a 2D view of the world, and then you were to draw the camera that's going to be viewing the world, right? Then if you were to kind of spread like rays away from that point where the camera is, and then kind of have like a second set of shadows, like 2D shadows in the shadow map, then all of the stuff that's shadowed, it doesn't have to be in the shadow map, because the camera is not going to view it.
All right.
Really. Yeah. So yeah, I mean, there's a you know, like there's a lot of stuff. Like if you were to draw the camera frustum, best case scenario, if you've got like a 90-degree field of view camera, is maybe 1/3 of your shadow map is not going to get used for anything, because a view frustum, unless you've got dueling froster, or you've got frustums which are concentric, then yeah, I mean, you might have 100% usage. But if you're thinking about, this is the sun and this is the camera, right? Then when you look down, it's going to be a triangle or like a trapezium, and that has to sit inside of a rectangular texture. So no matter which way you're going to twist the triangle, 30% or even more might not be used at all, because basically it's outside the frosting. And then we add onto it stuff like, you know, self occlusion and so on, or for example, you know, if your camera is against the wall, then, you know, for example, against the side of a building, then adaptive shadow mapping will give you a bounding box of all the stuff that the camera might see, but it's not going to be very tight. It's not going to be an oriented bounding box, or it's not going to be a convex hull. So the thing is like, even if you do use adaptive shadow mapping, there's still going to be like a lot of shadow map texels that even if you put, I don't know, floating point not a number in there, it's not going to affect your rendering at all. So I mean, a lot of work that you might do for a shadow map is going to be completely wasted. The memory, both the memory and the rasterization. So what ray tracing helps you do is basically you only send, it's fully adaptive. So you never send a shadow ray whose result that you're not going to use afterwards. A lot of the time, even most shadow map pixels are going to be shadow map pixels which you have rendered into the shadow map, but then you will never use. In some scenes, in some setups, it might even be a majority. So you're basically getting a lot of texel coverage in areas that don't need it, and then you're not getting enough resolution like where you need it near the camera, or in some really weird setups. So you get the aliasing in the shadow, and that's kind of like a wonderful thing that ray tracing lets you sidestep. And also, there's no memory. There are certain ways where you can do ray tracing which consume a lot of memory, like a wavefront ray tracer. But if we're talking only shadows, then there's absolutely no memory that you need to use for storing, all of the shadowing info. So you can basically just, no memory overhead and just trace the rays. The only problem between shadow mapping and ray tracing is that a shadow map is fully cached. So as long as the position of the light doesn't change, and the shadow map still covers the area that the camera can see, the camera doesn't go outside it, then you don't need to update the shadow map. You don't need to redraw it. So what a lot of games will do is basically, if a light doesn't move and nothing in the scene, like no shadow caster moves in the scene, no door opens, no character runs in front, then they will not redraw the shadow map. Or if they do redraw the shadow map, if the light is not very important, then they will maybe redraw a shadow map at 4 frames per second and not 30 or 60. It's a common optimization in cascaded shadow maps, where the first frustum that's near the camera you update every single frame, but then the last one, which is far away, you update every third or even every fourth frame. So that's not something that you're able to do with ray tracing unless you save the ray trace to a buffer and then reproject that, which is, it's feasible to do, but if you then start using ray tracing for all of the shadow lights, then that gets kind of complicated. But yeah, the ray tracing gets you, it's a lot better usage of resources. It's more focused. Like where you need the quality, that's where you spend the resources. And to make a really robust shadow mapping system, which can also do soft shadows, so talking about variance shadow mapping or moment shadow mapping, which I recommend over variance shadow mapping because variance shadow mapping bleeds, or for example PCF, then it's a lot of techniques which are approximations to the lighting equation, to the actual ways that the things are lit, that get stacked up on top of each other. So, if you wanted to have a state-of-the-art shadow mapping system, what you'd have adaptive shadow mapping. Then you'd have that into cascades. Then you rectilinearly warp those cascades. And then you'd render the shadow maps possibly into a sparse texture. So, some of the reads and writes get silently dropped for the areas that you're not using. So, you could use the adaptive kind of heat map completely. And then you'd blur the resulting shadow map for moment shadow mapping or variance shadow mapping, or you would do percentage closer filtering, and then that's its own little can of worms. And then you'd probably add some temporal reprojection if you're doing percentage closer filtering, because that's basically the same kind of noise pattern as you'd get in screen space ambient occlusion. So then it's basically like we're talking about maybe somewhere between 4 and 8 really complicated shaders that you'd probably want to optimize, and a lot of code inertia. If you wanted to change something, it'd be really, really hard for you to change. And I mean, thankfully, games are already stepping away from it, because you've got signed distance field shadows, which are basically poor man's ray trace shadows. So what you can do with signed distance fields is you can do cone tracing. When you do cone tracing, what happens is that instead of getting a binary visibility, or maybe like an approximated visibility in a tube, which basically what PCF is, you're able to get visibility in a cone. And what's really hard to do with traditional shadow mapping techniques is to get plausible shadows for area lights, because the whole kind of concept behind shadow maps is that the light is so small that we can render the scene from the view of the light and use the depth buffer to then query visibility between 2 points, between the point and the light. And once the light starts taking up an area, then you cannot really use a 2D orthogonal or 2D projective depth buffer to kind of, or cube map, to look up the visibility, because the visibility is no longer a binary 0-1. It's more like how much of the light am I seeing. And obviously in Crisis 3 and a whole bunch of games, there has been some things which kind of are nice, neat little hacks, like contact hardening shadows and what was it, PCSS, blocker search. So you're able to use something which is a little bit like percentage closer filtering, but it's basically, it's there to find the closest blocker, right? And then like how far away is the thing that's gonna block the particular light, and then from that distance you can choose the radius of blurring of the shadow map, and then that gives you contact hardening shadows. For example, like a shadow where if you've got like a chair and then you've got a shadow of a chair, like where the chair leg kind of meets the ground, you've got like a really crisp shadow, and then it kind of gets more and more fuzzy. So that's what they use. But the thing is, you can use that for the shadow lights. You can use that for the sunlight, because the sun is basically almost parallel rays. But the moment you start using it for polygonal lights, like lights which are disks, lights which are squares, stuff like that, it would all fall apart. And what signed distance field tracing or shadows or cone tracing lets you do is it lets you pick a cone that starts from the surface being shadowed, going all the way to the light, and then inside that cone you kind of get like an approximate occlusion, how much of that cone is kind of in free space. The problem is that it's not exactly accurate, and the footprint of the cone is always going to be a sphere, or basically a disk, a circle. So if you maybe wanted to have a rectangular light, or for example if you want to have like a strobe light or an office light, which is basically a very thin tube, then that wouldn't work. You'd have to trace multiple cones to get like an accurate shadow of that. So, but I mean, it's quite good for real time. It's quite good for games. In games, a lot of the time, what you do is basically you don't use, you know, tubular lights. You don't put like a glass door in front of a glass door. You don't put water in an aquarium. All sorts of things which are kind of corner cases, which you know that either you can't do, or if you wanted to do, maybe slow down the whole thing by a factor of 4. So artists have been trained to basically not create difficult scenes. So because of that, we were able to use sign distance field shadows to some success. Confetti effects with their little framework, the Forge. It's kind of like it's not an engine, but it's a thing they can use to make an engine. They have a sample where they have a sign distance field shadow for the San Miguel scene. So, and that also includes like the compute shader that kind of actually voxelizes the thing and computes the sign distance field, which is kind of a very interesting problem how to do efficiently in parallel on a GPU. So that's, if you wanted to do that properly, that's a very, very complex algorithm to do. And that's why Unreal Engine is using that and why Epic is using that in Unreal Engine for Fortnite. Fortnite's ambient occlusion is not screen-spaced ambient occlusion, at least not on PC. And the ambient occlusion is actually computed using voxel not voxel cone tracing of the sign distance field. So there are cones, a few cones around the point, which get shot out towards the world, and that's how they get the ambient occlusion and stuff for all of the buildings, and all of the structures that can be built in Fortnite, because global AO is much better than screen space. The interior of a like a temporary structure can remain dark even after you enter it, and there's absolutely no clues in screen space that you're inside of something. So that's really cool. And I think they also use a mixture actually of cascaded shadow mapping and sign distance field shadows. I think it's a mix, but they use sign distance field shadows like a lot. I think especially for the stuff that's far away. Or they had one demo where they used sign distance field for everything except for the terrain, because the terrain was a height map. So it's like a mix of two. But I mean, it's really performant. It's very nice, especially if you don't have some sort of a handicapped GPU like the mobile GPUs, or for example the Intel GPU. Some GPUs with actual onboard video RAM, so you got a decent enough texture throughput. You can have very nice shadows with sign distance field tracing, because it's basically just as expensive as parallax mapping. But ray tracing is obviously my favorite because it allows you to have arbitrary shaped lights. It's scalable, and it's actually very simple. I would say that building a bounding volume hierarchy and implementing rate reversal in that is possibly less complex than implementing the algorithm for computing a sign distance field from a triangle mesh. So I would say that ray tracing is my favorite here.
All right. So that was lots of stuff. That was great for me. And my question is, what do you suggest for the developers that are developing graphics, that are creating their own engines or working on some, for like today's architectures, technology, like what are the best practices, the best ways, the best options to choose and to work on?
Well, I mean, if you want to make a product as in a game that you want to sell, obviously Unreal and Unity are the two things that you could recommend. I would not recommend Unity because C#, and because, I mean, unless you want to make web and mobile games, then I guess Unity is good. But if you want to have a high quality PC or maybe Xbox or PlayStation console product, I'd definitely recommend Unreal. Simply because Unreal seems to have a little bit more features. Possibly, I mean, the performance of the two is on par, but you definitely get a lot more. I want to say access to the low level, but I would say you basically get a lot more power out of really powerful hardware. And the other thing is like Epic actually makes a profit, whereas Unreal, whereas Unity, they only profit they haven't made a profit yet, I think, if I remember correctly. They do make really nice R&D, like for example, the papers on lighting by Eric Heitz and the stuff that comes out of Unity research is really top grade. I haven't seen anything like that coming out of Epic. So they're definitely doing a lot to advance the field. But the the main thing from which Unity gets money is basically in-game ads. And that's basically where all of the millions come from.
All right. And what about if someone tries to make their own graphic API or their own engine? Like, what are the ways you suggest?
If you want to make your own graphic API, you should join the Web GPU gang. So that's the current party going on. If you want to make your own engine, you have to have a good reason to do it. I guess there in the community of graphics programmers, a lot of people do shit on Unreal for being huge, complex, taking a long time to compile, and absolutely a nightmare if you want to actually get anything done in your own way or scalable. So yeah, I mean, the Unreal doesn't have a lot of love in that circles. But if you for example wanted to make something that would be difficult to make in Unreal, or for example if you didn't want to have your whole app or your whole thing be a plugin in Unreal, because we should remember that Unreal is an engine, it's not an SDK really. So Unreal is not for embedding in another application, and so isn't Unity. So unless you want to, go digging through heaps of code to make it embeddable, or basically rewrite if you already have something, write your application as a whole bunch of Unreal plugins, which you kind of all then have to be kind of fold somehow into the editor and get built and packaged by the editor. To make a release, or for example, the same problem you have in Godot, and actually the problem in Godot is actually much bigger, because then you have to write the whole thing in Godot script or whatever they use down there. At least in Unreal you can write your plugins in C++, and in Unity and C#. Yeah, so if you wanted to make something that isn't just supposed to be a plugin and run inside of the editor, get booted up by the editor and kind of package as the engine runs your code, not your code runs the engine. If you want your code to run the engine, then and you've got a good reason for that, that's kind of the place where you'd want to consider making your own engine. And I mean, if you're not making a first-person shooter, if you're not making a point-and-click adventure, if you're not making, if you're not making a strategy game, for example, because I think strategy games are absolutely fine to make in Unity. But if you're making something that really falls outside of that scope, then that's the time to make your own engine. If you're making a flight simulator, I don't think Microsoft Flight Simulator could have been done in Unreal, right? If you're making something that requires a lot of streaming of assets, and if you for example were to make an MMO, then that would most probably not be well served by the current engines. If you, for example, wanted to make an application which is not a game, or if you want to make a complex web application, which kind of integrates with a whole bunch of other stuff, then that most probably wouldn't be the place to use Unreal or Unity. Or, for example, if you only wanted to make something that renders, right? Then that's maybe not the place to use Unreal or Unity. And so far we've always been in those two categories. It might change. But yeah, I mean, if you basically have something that requires massive worlds or doesn't use big parts of Unreal or Unity that take a lot of resources from your system, if you are, for example, focusing tightly on a single platform, then that's probably where it would make a lot of sense to have your own engine.
All right. Yeah. So, what are you aiming for right now with your Nabla?
Okay, so we've got this problem, generally speaking, with a whole bunch of, because you shouldn't really go and reinvent the wheel. Reinventing the wheel gets nothing done, costs a lot. I mean, if you're on schedules and you actually have to deliver stuff for money, then you shouldn't be suffering from the not invented here syndrome. So stuff that I've seen succeed and not be based off Unreal and Unity usually uses a whole bunch of frameworks. For example, everybody uses Vulkan Memory Allocator. Everybody, maybe not everybody, but a lot of people use the NTT system, the ECS. I don't think I've ever seen anybody do 3D physics that wasn't based off Havoc or physics or Bullet. That's, to make your own physics solver is insanity. I've seen even less people try and cobble together their own audio engine. I mean, everybody uses OpenAL, SDL Audio, or FMod. FMod actually I recommend, unless for some reason you're not okay with the fact that it's closed source and you actually have to pay for it once you start selling enough. All of the stuff is basically it's good to use. I know a lot of game programmers like to shit on SDL. Sorry, not on SDL, on STL, the standard template library, as well on Boost, but those two can be very useful. And STL since C++11 and C++17 with stateful allocators is actually not that bad. The only thing that needs replacing is the unordered set and unordered maps, which are supposed to be hash maps, but they have some certain design quirks which prevent them from being efficient. So yeah, generally speaking, if you can find a library for something, you should use it. And the main issue is that there's a lot of 3D engines, a lot of hobby 3D engines, a lot of 3D engines that were started and kind of went dead because either they went into a dead end, developmental dead end, where if you wanted to proceed, you'd have to redo a whole bunch of stuff, or they didn't progress fast enough to keep up with the alternatives. And I mean, there's heaps and heaps of engines that are either abandoned, never reached usable state. I think almost everybody in the graphics programming community that I know has their own engine that they were or are working on. And I think 80% of them have never been used to deliver a commercial product. And then you've also got all of the engines which used to be great, but then got absolutely wiped out by Godot and Unreal and Unity. So Irrlicht is so far behind. It's impossible that it will ever catch up with anything. Ogre has been going quite slow, and I'm talking about graphics engine obviously right now. Horde 3D is basically, you can't make anything out of that because everything is basically an asset that goes through XML, and there's nothing for you to grab onto on the C++ side that is a publicly available API that you could then do stuff with. So, I mean, Horde 3D is not a 3D engine, it's a 3D viewer. Because, you couldn't, for example, you can update a part of a mesh. You couldn't do any transformations with a mesh. You couldn't stream a texture. Like, for example, we needed to stream textures into TVs. Like, you can't even you can't even go into it and have control over what gets drawn when. So that's I wouldn't even call it a 3D engine. Or how 3D, I don't know how that looks right now. Wicked Engine kind of looks like the same thing that I'm doing by some sort of consultancy, but looks like it never got organized, and the main guy behind it is now a programmer at Sony Studios, so I don't think he has time to work on that. Plus, it's DirectX only. Then you think the only one is like Amnesia 3D or something like that, or sorry, Ankh 3D. So that's actually made by some graphics developer / researcher, but none of them is really like, all of them start off with the same assumption that you're either gonna have a scene graph or you're gonna have some sort of an entity system, and you're gonna have a bunch of things to draw, and you're gonna have a level, and they kind of already they want to be in charge of the high level stuff, right? And the whole, like, that's the same idea behind Unity and Unreal. You already have actor objects, you already have nodes that you can kind of transform and move around. And if you already have an engine that kind of want to go that route, where you've got different objects, and then you already kind of like, they already give you like the gameplay API that you want, as in you have objects to move around and they have different materials, but they kind of like have all of this under the hood, and then the API doesn't really let you do stuff with the internals. Then the question is, why would you choose that over Unreal or Unity? Because it's like the same feature set, it's the same kind of, almost the same philosophy. And a lot of the engines that I've seen, I mean, for example, Banshee 3D, which is something, very nice project that I've seen. So Banshee 3D is basically like, yeah, we also have an editor. We also have like a node programming graph. And, like the whole thing looks like Unreal, but it's basically the same. So what happens is that there's basically like a disconnect, because all of those things are already doing what Unreal is, but on a smaller scale. So I was saying that Banshee 3D has this nice editor, and the main issue here is that with the fact that it has like all of the same buttons and like the whole interface, this is especially the problem for me. That's the problem with Godot. I like the fact that Godot exists because it's a free alternative, that's not proprietary, it's not encumbered by anything. So it's like a nice free alternative to Unity and Unreal. Should, for example, Unity go bust at some point because they're not making profits. So Godot is nice that it exists as an alternative, but then everybody trying to copy that or kind of go into the same kind of mode where, we're going to do all the graphics for you. For me, it doesn't add anything for the developer. It doesn't actually save me any time, because the reason why I'm not using, for example, Unreal or Unity might be because I'm making something that's just not going to work there. So if I'm making something, for example, where the whole world is destructible, for example, think about Roblox, right?
Yeah.
I'm going to hold up Roblox as a better alternative to Minecraft. So Roblox has like this whole dynamic world and everything. You couldn't make that in Unreal, not with the same performance, because you know what this thing is going to do. So then you build all of the infrastructure around it so that it's made for the purpose. so it's streamlined for that. If everything in Roblox was running through Unreal scripts and had to fit into the Unreal shaped holes that the APIs provide, it'd most probably be 2 or 3 times slower, right? So if you're gonna say, I'm not gonna use Unreal or Unity because I don't know, I need 1,000 units versus 1,000 units fights, of skinned meshes, or I'm making something that has to run, really quick and smooth on phones because I'm making no, like a multiplayer, battle arena. Or if I'm making like a flight simulator, right? I've given you a whole bunch of things which are very like kind of constrained and specific, like purpose specific. And the main problem here is that if you're going to take one of those uh, popular open source engines or alternatives or frameworks, then if something already works on a scene graph basis where you load an asset from an OBJ and they already give you all the shaders. So for example, you can swap out a shader for something else. And there's no distinction between loading a frame from disk and having it on the GPU, or the scene manager is already done. Or, for example, this is the sins of Ogre, right? We've got all sorts of nodes, scene nodes. Yeah, there's a bunch of nodes, and you can kind of move them around. Then it gets really hard to implement stuff, for example, that can stream in textures, or that can stream in objects, or level of detail, stuff like that. All of those things, in order to implement them, you have to rewrite the engine. Or if you wanted the different lighting methods, for example, if you say, I don't want deferred, I don't want forward plus, but I want visibility buffer, or I want ray tracing, you'd basically have to throw away half the engine because the author of the engine has already written deferred rendering for you, or forward plus. And I mean, all of those engines, they have really nice screenshots. They look really nice. Mine doesn't look that nice. Because they've got like a scene, and in the scene you've got lights, shadows, screen space, ambient occlusion, depth of field, and everything. But all of that is already coded for you. And the minute you want to start moving things around and changing things or optimizing things, then you suddenly realize that there's more friction for you to get them done by getting them done through the engine than if you were to write the application from scratch by yourself. And that's, I think, part of the reason why there are so many graphic engines and graphic engine projects, and why everybody is reinventing the wheel and working on their own thing. Because the minute they want to use somebody else's, they find out that it's actually harder to get it done in somebody else's than if they were to write it from scratch. And this whole picture kind of brings together what I'm doing with my own framework. So what Nabla is basically, it's not supposed to render your scene for you. It's supposed to be a stepping block between the graphics API or the graphics APIs that you're going to use and what you actually want to do. So it's designed for a person who would want to write that whole thing from scratch, right? But wants to basically get a leg up, right? Who wants to, for example, already kind of latch onto things that are already working. And I think the only other two frameworks which kind of do that is BGFX, which is called Bring Your Own Graphics Framework by Bogdan Karadžić. But the thing there is actually it's only a wrapper around Vulkan, DirectX, and everything else. So what it does is basically it wraps around all of the APIs and lets you use this one kind of front end to do everything like in a cross-platform way, which is it's nice. And then you've got Confetti FX the Forge, and the Forge is quite strange. I've worked on it a little bit, and I'm not bashing it. I really like it, and I've got tons of respect for the authors. But it's there to solve a completely different problem, and I think it's mostly so they can do their prototyping because they work on AAA games, so they already have some sort of a thing to do prototyping in, and do all sorts of things, and then kind of move that over and implement it in other engines. So it's basically a well-maintained collection of libraries, because they use a lot of libraries like Asimp and stuff like that. So it's a collection of libraries that can make it quite easy to put together proof of concepts in DirectX 12 and Vulkan. But the thing about its API is actually it's not cross-platform. The API is kind of cross-platform, but there's a lot of things which are, for example, if you want to use DirectX and use Vulkan, you kind of have to write specific parts, which is nice. I must say it's very nice, because it's for the low-level programmers who, like me, know what they're doing and they want access to the stuff, and they don't want the API to wrap it in 5 layers of abstraction, and then if you want to add like one more feature, then you have to like go through all those 5 layers of abstraction and kind of fix up all of the things that would break it, right? So in that case, I think Confetti FX is the Forge. I mean, it does a good job at what it's doing, but I mean, it's not gonna, aside from Asimp, it's not gonna load your assets for you, and then it's basically like BGFX on steroids, plus they've got a whole bunch of useful examples to go along with it. But yeah, I mean, it's definitely, it's definitely something that I would use, and I think it's the fact that they've got so many people in that company working on it and kind of like adding things onto it makes it very, very appealing to use. But the main reasoning behind why I'm working on my own framework is because it solves things which are specific to what I'm doing. So, for example, it's quite close to the concept of the Forge, but one of the cool things that for example I'm doing is I'm taking GPU programming seriously. So in most engines, what you'll find is that most engines, for some reason, because they suffer from not invented here syndrome and they really want to reinvent the wheel, they have their own shader languages. Unity has its own shader language. Unreal has its own shader language. I mean, you can make shaders out of, graphical blocks. Godot, I think. Now, Godot is OpenGLES, so it takes GLSL. But a lot of engines have their own shading languages for absolutely no reason. And one of the cool things that my engine does is basically it ingests either GLSL or SPIR-V. And by the fact that it ingests SPIR-V, it also means that it can ingest HLSL. And from this ingested SPIR-V that it always takes as like the middleman, it can produce all of the other ones. SPIR-V can go to Vulkan. From SPIR-V, we can generate pretty good OpenGL, GLSL to go to OpenGL. And in the future, I guess through Molten VK and stuff like that, it's also going to go to Metal or, anything else that we might need, because SPIR-V is an intermediate representation, so it should be pretty easy and straightforward to compile down to anything else like NVN or whatever the console API we're thinking about. And the other thing that we're also taking seriously is that I think we're the only framework that has interoperation with CUDA and OpenCL, both of them at the same time. So the way that this works is you can make a GPU buffer, and in our engine, this is an object which is like a first-class citizen. Everything else you want, you make out of the GPU buffer. Everything basically comes back to a GPU buffer or like a GPU image. And then you can basically register that with the CUDA handler of interoperation or the OpenCL handler of interoperation. And you can get CUDA or OpenCL handles for those buffers. And this is the same buffer that is on your GPU that you can use for rendering operations. So, for example, because of that, in our framework, it's really simple to use Radian Rays, which is an OpenCL, the open source version anyway, together with the rasterization. So you can build a hybrid renderer really quickly. Or, for example, you can use the optics denoiser. We have 3 samples, soon 4, of interoperation with CUDA. One is where you basically can run a CUDA kernel, which takes OpenGL, our engine's GPU buffers or GPU images as input. Another one, which is basically the optics AI denoiser, where you can feed our engine a noisy EXR with multiple layers, with albedo and stuff like that. And then it will denoise it for you. And then we're basically working on 2 other ones where a number of other examples which demonstrate interoperation with CUDA and optics. So we're working on a basic optics integration sample where you use our engine to load all of the models and send them to the GPU. And then you use optics to just build the BVHs and actually do the ray tracing. And then we've got basically an optics path tracer in the work. And that's actually like an actual thing that we're making for a client, which is basically going to render very complex scenes with path tracing. And the Radian Rays we kind of put in as a courtesy, as like a proof of concept that we could do ray tracing on the GPU. So that's not something that we actively want to maintain for a long time, but it's there. And it's basically using Radian Rays to build a BVH and then send some rays. And we actually, because of the interop with the rendering part and the OpenCL, we actually have a hybrid renderer where it's making a visibility buffer, like a kind of like a G buffer visibility buffer. It's generating the rays to send and into a GPU buffer, and thanks to OpenCL interop, it hands over that buffer to Radian Rays to do the ray traces on, and then the Radian Rays writes out all of the informations about which object triangles and where the ray trace part has hit, and that gets passed back to a compute shader, which is now in OpenGL in our engine land, and that compute shader uses the results of the ray trace to do the lighting. And that's something that you can't really do with any other engine out there, because I mean, if you can, then it's so tightly coupled that you don't have access to the in-between stages. And one of the main things that we're going towards, because this is a fork of Irrlicht, it's like very continual change of source code. So one of the things that we're trying to do is we're making sure that you can split this in 6 different libraries. So we've got the core library, which handles stuff like memory allocation, alignment, vector types, containers, all sorts of things that you don't even need to know what system this runs on. And then we've got the system library, which should handle all of the file IO and stuff like that. And that's kind of in the works, because file IO and all sorts of stuff that we like, that is basically stuff that we've been neglecting. And then we've got the UI library, which is mostly to do with keys, gamepads, mouses, and windows. And that's going to be built on top of EGL and SDL. And then on top of that, we've got the asset loading part, which is pretty much finished. We're just looking to do a little bit of an upgrade so it can work better and safely with multi-threading. So you can use multiple threads to load assets. And that basically loads your textures and your models. And the cool thing about it is that we've actually designed a proper system. Every single other kind of open source engine or kind of engine project out there is basically a hobbled together like a duct taped asimp with STB image. They don't really care about not reloading the same mesh. They don't care about not reloading the same texture. They don't care about the fact that two meshes might use the same texture and it would be nice to spot that. They don't treat they don't treat a shader as an asset. So shader is not an asset that you can actually load from a file. A whole bunch of things. And then we actually do all of that. So everything is an asset, and every single GPU object, we're talking textures, buffers, buffer views, image views, shaders, specialized shaders, pipelines, descriptor set layouts, descriptor sets. And we're eventually aiming towards command buffers and render passes. But all of that is an asset, and all of that can exist as a CPU image, which is mutable, as a CPU thing, which is mutable, which exists on the CPU, independent of the graphics API. And you can kind of push those to the video part to get your API objects, and also kind of sometimes download them so you can then save them to file. And that's very important because nobody else has this. Nobody actually went to this trouble because we've actually had to use this whole system, everything, in an actual product. And then those were the lessons learned, that you need the system to kind of handle, loadings for stuff from disk. And also it's important to have a distinction between a CPU representation, like a mutable representation of a thing, and a GPU representation of the thing, because what you might be able to do with the GPU representation might vary backend to backend. And also, for example, if you want to have a server application or something like that, you will rely on having a graphics card to, for example, process a mesh, to do an image blur, to compute bitmaps, and so on. And what we do is, yeah, sure, you can use the GPU for those things, but we also have all of the mesh manipulation. I think my camera doesn't want to work.
Okay.
the low battery. But yeah, basically we have a image manipulation, blurs, all sorts of convolution kernels that you can do on the CPU side reliably and portably. So you can always do this thing on the CPU if you don't have a GPU available. So that's kind of the whole logic behind it. And also, we don't believe in providing you the graphics, the solutions, the rendering algorithms hard-coded into the engine. So we'll give you an example and a whole bunch of utilities to, for example, do bloom, screen space ambient occlusion, ray tracing, and so on, but we're not going to build it into the engine. We actually have the engine do those things for you. So it's basically the logic and the whole philosophy behind the engine is assembly required. I don't know if you've ever seen the Google assemblable phone project, where you could assemble the phone out of different pieces. If you wanted
no, I haven't.
a better camera, then phone blocks. So basically the idea is we're not giving you a prepackaged phone where a certain CPU has been put together with a certain GPU, with a certain RAM, with a certain battery, with a certain screen, and then there's nothing you can change. So we give you all of the components separately, and then you can put together out of that whatever you want. And I think that's the main idea. We're not there to create friction for you for an implementation of something, right? As I said, given the previous examples, if you wanted to change something in an engine, like how it renders, how it shadows, you would basically spend more effort than implementing the whole thing from scratch yourself, with basically giving you all of the different tools and components, so there is no friction. And one of the great testaments behind that is basically that we do have a GLSL compiler embedded into the engine, which can resolve include directories and all sorts of things like that. And we actually provide a GLSL library, which right now is about 5,000 lines of code. And it has all sorts of primitives that you'd really want to be able to use. So, for example, work group scans, subgroup scans,
portable, obviously, not relying on extensions. They are accelerated by extensions if they're available. Um, the tone mapping, just the code, the GLSL code. It's not like, oh, you now need to use this module and set up all of the buffers for it. You can override the buffers. You can override the inputs. You can override the outputs. You can override everything. We give you the conversions between the different color spaces and the XYZ color space, different OOTFs and EOTFs. We will soon provide the fast Fourier transform as a GLSL header that you can just basically include and kind of use. We provide pretty much every single reasonable BRDF and BSDF model on the planet. So we're talking everything that Mitsuba has. So we're talking GDX, Beckman, PBR, dielectric coating on top of a diffuse, rough diffuse, rough glass, thin glass. We provide all of those model functions, and not only that, we also provide importance sampling functions for those, so you can actually use them in a ray trace. And all of that is available as a GLSL library, as well as a whole bunch of other things for example, generating random number sequences that you might want to use for the ray tracing. And all of that is available as a library, as opposed to being one integrated thing that is really difficult to, chop together and then modularize and reassemble into something else that you might like. Yeah, I mean, the main assumption is that the user is already the kind of person who would basically write their own thing from scratch. And it's there to make that user's life easier. So, we can already load stuff from file, compile shaders, and then, given your GLSL or SPIR-V shaders, we can build all of the stuff like descriptor sets or pipelines, approximate pipelines from the shaders that you provide. So you don't have to write a whole bunch of boilerplate. We also provide memory allocators. And I know that I said about not suffering from not invented here syndrome and from reinventing the wheel, but we had a good reason not to use VMA, which is basically A, that we weren't using Vulkan at the time, and B, we only wanted the allocator part. And C is that most allocation libraries and most things that implement allocators, they don't separate the allocator state from the thing being allocated. So it's mostly about allocating out of arrays which are accessible by the CPU, but we can allocate anything. We can allocate IDs to use slots to use in a shader for object data and SSBO. We can allocate parts of textures, for example, for virtual texturing. We also have like an implementation that you can use for virtual texturing. We can allocate bits of buffers. All of that stuff is really, really useful. So it's basically, and that's kind of why we didn't use VMA. So it's basically there for that person who'd want to write stuff from scratch, but basically help them along and get that leg up. So maybe they don't have to write an allocator. Maybe they don't have to write all of the material models, because material models are hard to write, and then also to validate that they're actually doing what they're doing. There's only one way to write a material model. If you're saying this is GGX with height correlated Smith masking and a real an imaginary Fresnel function for a conductor, then there's only one way to write that. And you might write that and then get a bug in it. And if you're going to use it in a ray tracer, then you might be scratching your head for a long while before you actually notice that, hey, maybe my importance sampling function doesn't actually match the evaluation function that I wrote. Right?
Okay.
So that's kind of very useful that this is already written down. And even if you're not going to use the library itself, it's also useful with the fact that it's so modular that you can just basically, maybe take a few sources from the library and use them in your own project. For example, most of GLSL code that we write, you could pretty much just, copy out and use somewhere else.
Okay, so that's like really helpful from like the point of view for the developer. And yeah, thank you for like all those things related to the tricks, the tips, and thank you for joining me here. So
Yeah, no problem.
that will be it for that. And yes, again, thank you. So I will try to later cut it and put some background because your camera was dead, but I think I can handle that.
Okay. My phone's about to die.
Okay. So yeah, have a nice day. Bye.
Bye.